Alright, so what we're going to do is look at the indefinite integral, and these are basically antiderivatives. One of the biggest deals that we need to try to remember, though, is this plus c, which is the constant at the end. The derivative of every single constant is 0. So when you evaluate an indefinite integral, you can always check yourself by going back and looking at the derivative of your answer. And if the derivative of your answer is the number inside the, or the function inside the integral, everything is great. So let's go ahead and look at an indefinite integral here. So I've got the indefinite integral of x squared minus sine x. Well, when you're working with integrals and you've got exponents, then you're going to add 1 to that exponent when you integrate it. And 2 plus 1 is 3. And then you divide by that new exponent. And then minus, and then the derivative of what thing is negative sine. And the answer to that is negative cosine x. And so plus c at the end to account for all of our constants. And we can clean this up one step by just saying we've got x cubed over 3 plus cosine x plus c. And if you check this, if we take the derivative of x cubed over 3 plus cosine x plus c, and remember c is any constant, then what we have is 3x squared over 3 minus sine x plus 0. And when we simplify that down, you get back to where you started inside your integral. So that's all there is to it. It can be very complicated. There's a lot of different things that you can do, but on some of these introductory problems, you're just looking for the antiderivative and a constant. Okay, here are a lot of rules for working with indefinite integrals, and you might want to pause the notes right now and write all these things down. They're going to come up in different ways at different times, in different shapes, in different forms, and so this is just one snapshot of everything that you can do. So pause, write all this stuff down, and then we're going to look at how all this stuff goes on the next slide. Okay, so here we've got a couple of antiderivative formulas to look at, or definite integral formulas to look at, and the first one deals with the indefinite integral of u to the negative 1, which is the same thing as 1 over u. And we want to show that this definite integral solution works, like that this is a completely true statement. So there's two cases to consider here. One is that u is going to be greater than 0, and one is when u is less than 0. And remember, when you're talking about natural logs, you cannot have a natural log of a negative number. Okay, so that's why the absolute value part is important. So you can then just take the let's just take the derivative. Let's look at this guy as natural log of u, and when you take the derivative of that, you're going to have d dx of natural log of u plus c. Okay, and so this turns out to be then 1 over u du dx plus 0. And du dx in this case is just going to be the derivative of u, which is 1. So 1 over u times 1 plus 0, which is 1 over u. And hey, guess what? That's where we started. If u is less than 0, then when we take the derivative of that guy, then what I've got is I've got the natural log of negative u plus c. And so then what's going to happen is I'm going to end up with 1 over negative u times du dx plus 0. And then when I look at my derivative of u, the derivative of u is going to be negative 1. So I've got 1 over negative u times negative 1 plus 0. And this is going to be just 1 over u, which also is what we had. So these two guys right here are just kind of show you several different ways, or not several different ways, but a couple different ways to work with definite integrals and working through the derivatives and all that kind of stuff. So it's really kind of interesting stuff. All this stuff should relate and go back together, and that's what we're trying to show with this proof. So the other one. Okay, so on the next example here, we're going to again start with what our definite integral equals, and we'll see if we can't take the derivative of that and get back to the original problem inside the integral. So one thing to just be aware of as you get started is there's a product rule that's going on right there. So that's going to be something to pay attention for. And when I do my math, I got d dx. And now I want to look at u ln u minus u plus c. So I want to take the derivative of all of this, keeping in mind that the product rule is occurring on this part of it. Okay. So the derivative of the first times the second is 1 times natural log u, plus the first times the derivative of the second, which is going to be 1 over u, minus 1 plus 0. So that's what it looks like when we take all of our derivatives. Simplify this down just a little bit. 1 times natural log of u is natural log u, plus u times 1 over u is 1 minus 1. And hey, looky there, the 1's go away, and I'm left with natural log of u. So that's how that guy works out. Again, it's really nice and easy to be able to go back and check all these. So anytime you look at a definite integral, you should always be able to differentiate your answer and get back to the function that you started with. Okay, here's some problems that are going to require us to pay attention to the differential of what's going on and making sure that all the correct variables are in the correct places and we're doing the correct thing. And this can get confusing, so pay attention to exactly what you're working with. In this first guy, write down what you've got. We're looking at, on this very first problem, the integral, the indefinite integral of f of x, which is x cubed plus 1 dx. That's what we're working with. And when we integrate this, we're going to end up with x to the 4th over 4 plus x plus c. That's all there is to it. There's no trickery going on. All right. Well, what about the next guy? We're looking at f of u du. So the definite integral for this guy is just replacing the u in the function. So if I've got f of u, then what I have is x cubed plus 1. Okay. And so now when I look at that guy, I go, all right, I'm looking at x cubed plus 1 du. Okay. And so when I integrate that guy, by the way, terrible. These should be u's. Here we go. Because we're replacing the x with a u. So again, I'm going to end up with u to the 4th over 4 plus u plus c. But we're not quite done yet because we're told that u equals x squared. So everywhere that I see a u, I put an x squared in. So I've got x squared to the 4th over 4 plus x squared plus c. And so this guy actually is going to end up being x to the 8th over 4 plus x squared plus c. And that's the middle guy. Now the last guy is really interesting, okay, because we're looking at a function of u, which we wrote down here, a function of u. Okay. However, the variable of integration is this dx part right here. So once we get our function of u written down, we're going to have to substitute in the x. So this is going to look really strange. But to start off with, we're looking at the integral of u cubed plus 1 dx. Now, the dx is important because all of the variables need to all be x's. So what does u equal? Well, u equals x squared. So we're really working with the integral of x squared cubed plus 1 dx, which is really the indefinite integral of x to the 6th plus 1 dx. And so when we integrate that, we add 1 to the exponent, divide by the new exponent, and add our constant of variation. So again, just pay attention to what's going on and make sure that all the variables match inside your integral. Alright, what we're going to do with these next few questions is look at how to sort through some substitution problems. If you think about what you can integrate or take the derivative of that gives you e cosine x sine x, it becomes very challenging because the chain rule is involved. And so working backwards from that can be really, really, really tricky. So what we're going to do is we're going to pick a u. And in this particular case, I want it to be cosine x. And the more you work these, the easier it'll get to see what you need to do with your substitution. And then I'm going to look at what du dx is equal to. And the derivative of the cosine is negative sine x. Okay? And so go ahead and make du by itself. So this is going to be negative sine x dx. Okay? And then if you'll notice, if this is what du equals, then I've almost got that right here. The only thing I need is that minus sign. So I can put a minus sign in here and get this. And then notice also that this u for cosine x is going to go into this position. So what my problem actually is going to turn into is I'm going to put a negative sign in front of, I'm going to account for the negative sign. Okay? And my integral becomes negative, the indefinite integral of e to the u, okay, times du. Okay, this is what it's going to look like. And notice that if I distribute this negative sign in the front, back in, I get back to where I originally started. Okay, which is why, you know, it's important to have that. When you substitute, you need to be able to get back to your original guy. And so now my integral then becomes negative e to the u du. And this is great because when you integrate e, you're just going to get e to the u. So this is negative e to the u plus c. And then what was u? That's cosine x. So my final answer then is going to be negative e to the cosine x plus c. So that's how my substitution would work. Okay, so let's look at another one. Right here, I've got the indefinite integral of x squared times the square root of 5 plus 2x cubed. And so now what? Well, let's try a substitution of u equals 5 plus 2x cubed. And so du is going to be 6x squared. All right? And go ahead and get du all by its, this is du over dx, by the way. So go ahead and get the du part all alone. And what you're going to end up with is du equals 6x squared dx. Okay? And so if I'm going to add that 6x in here, just like I did on the previous problem, then I'm going to have to multiply by 1/6 in front of my integral. So watch, here we go. I'm going to add my 1/6 here, and then I'm going to have the definite integral. Okay, can you see it now? Of du dx, which is the 6x squared dx part, the du part, times the square root of u. Okay. So this looks really strange, but I wrote it that way for a reason, because here's what you're going to end up with: 1/6. And notice when you multiply 1/6 with 6, we're back to our original equation. So what I'm really doing is I've got the indefinite integral of the square root of u times du. Okay. So this is really 1/6 times the indefinite integral of u to the 1/2 du, and you just add 1 to the exponent, divide by the new exponent, so this is 1/6 times u to the 3/2 divided by 3/2 plus c. So how does this really look? Well, you've got multiply by the reciprocal, so I really have, I'm going to multiply by 2/3 here. So I'm going to end up with 1/9 u. Okay, what was u? U is 5 plus 2x cubed. 1/9 5 plus 2x cubed to the 3/2 power plus c. Let's look at one more guy. Cotangent 7x. So, looks a little tricky. Let's use a little trig identity here. And let's just think about this guy in these terms. The indefinite integral of cosine 7x over sine 7x dx. Now one of those is the perfect derivative of the other. And so what I would recommend is that you let u equal sine 7x. Because du dx is going to be cosine 7x times 7. So du is equal to 7 cosine 7x dx. Okay? Alright, so how is this going to look? Well, if I've got this 7 here, I've got to put a 1/7 in the front of my integral so that they'll cancel out. And I'm going to have my du dx, here's my du, over my u. Okay, do you see it? In other words, what I'm working is 1/7 times the integral of du over u. Okay? And when you integrate 1 over u, that's just natural log. So I have 1/7 times the natural log of u. And it's got to be absolute value because you cannot take the natural log of a negative number. Okay? And so what is my u? My u is the sine of 7x. So my finished answer is 1 over 7 times the natural log of the absolute value of u sine 7x plus c. Okay, so one trig problem isn't enough. Here's 3 more with some u-subs in tow. And, you know, the dx over cosine squared 2x, not one I carry around in my back pocket. But an equivalent statement to this would be secant squared 2x dx. Now, this has promise because I know how to integrate secant squared. Secant squared goes to the tangent. Well, how can I get it to just be secant squared of x? I'm going to let u equal 2x. And so du dx is going to be equal to 2, which means that du is equal to 2 dx. So if I'm going to add this 2 in here, I've got to put a 1/2 in front. Alright? And watch this. The hand is quicker than the eye here. I'm going to have 1/2 the indefinite integral of 2 secant squared u du. Okay? And so, wait a second, that 2 doesn't belong. Let's get that guy out. The hand truly is quicker than the eye. I'm going to have 1/2 secant squared u du. This is one I can solve out. In fact, it's going to be 1/2 times tangent u plus c. Well, what is u? U in this case was that 2x. So my final answer then is 1/2 tangent 2x plus c. So really, he's not too bad. Pretty doable. What about this cotangent squared 3x? Well, again, the cotangent squared can be rewritten with one of our trig identities, and they are the ones that relate us all the way back to sine squared plus cosine squared is equal to 1. So when you go back and review all of these identities, one of those identities is this one. That, if you go back and review, one of the identities is that the cotangent squared of x is equal to cosecant squared x minus 1. And so cotangent squared x is not one that I carry around in my back pocket, but maybe somehow with the cosecant in there, life could get a little bit easier and more bearable. So how would this look? Well, instead of just x's, I'm going to have 3 x's. Okay, so this shape then is going to take on the look of the integral of cosecant q squared, cosecant squared 3x minus 1 dx.
Now that I have switched out the identity, we know what the integral of cosecant squared of x is. We know what the integral of 1 is. What we need to do is use U-substitution so that instead of having 3x there, we just have one letter. So like u needs to equal 3x. Okay, and so then we take the derivative of u, and we get the derivative of 3x is 3, which we would then rewrite that as du equals 3 dx. So, if I go back and put that into my integral now, I have cosecant squared of 3x. I'm going to put a u where 3x is, so that's cosecant squared of u, and then minus 1. Now for my dx, I'm really putting in du over 3 for my dx. So if I put in du over 3, then I'm going to put a du here, but instead of the over 3 going on the inside, I'm going to make it a 1/3 on the outside. So now we're ready to take the integral. We're going to have a 1/3 out here. The integral of cosecant squared u is negative cotangent u. The integral of -1 is negative u. Okay, and then we need a plus c, because that's what we do with integrals right now, right? Is we put a plus c. It's an indefinite integral. And now I can distribute the 1/3, and I also need to switch back to my x's instead of my u's. So we would say this is negative 1/3 cotangent, but instead of u, I'm going to put a 3x, minus, now u is 3x, but I'm timesing that by a 1/3. So I've got negative 1/3 times 3x. 1/3 times 3 is 1, so I could really erase that and just call it x. So minus x, and then it's plus c. So that would be my answer right there. Alright, this last one, the integral of cosine cubed x dx. The trick on this is for us to think of it like cosine squared x times cosine x, so that we can use an identity. Remember that cosine squared x plus sine squared x equals 1. And so what I'm going to do is I'm going to change cosine squared x to be 1 minus sine squared x. Okay, we might say, how is that helpful? Remember that the derivative of sine is cosine. So if we let u be sine of x, then we take the derivative of sine, we get cosine, which then we can rewrite as du equals cosine x dx. Okay, well, let's look at what that's going to be if we do U-substitution. We've got, for sine x, we're going to put in a u, so that's 1 minus, we have sine squared, so that's u squared. The cosine x dx is the same thing as what we have right here, so I'm just going to replace that with du. Now this is something that I can integrate. Okay, the integral of 1 would be u. The integral of u squared would be, we add a power and divide, so that'd be u cubed over 3 plus c, and then we plug back in our x's, so, or what we had as our u, sorry. We plug in u equals sine x, so that's sine x minus sine cubed x over 3 plus c. Or we could write that as 1/3 sine cubed x if we wanted to. But that's our answer on that one.
Okay, so let's look at some more U-subs, and this time let's check them out with definite integrals. So the first guy here that we've got is tan x secant squared x from 0 to pi over 3. Okay, not a big deal, but in order to pull off the U-sub, we've got to look at these guys. Like I've got a tan x here, and I've got a secant squared here. One of those is the derivative of the other, so we just need to figure out which way that goes. Well, if you look at your trig card or whatever, if you take u and let u equal tangent x, then the derivative of that is secant squared x. And I'm going to go ahead and move the dx over here. We've done several examples. This is where we have to ultimately be. I'm just going to go ahead and write this secant squared x dx over there. So now what have I got? Well, now I've got this integral from 0 to pi over 3 of u du. Now there's a couple places that there's a couple things that we can do here, and one of them is to go ahead and change our limits of integration, because then we won't have to do any substituting when we get done. We'll already have taken care of it, and this really can make the problem quite a bit shorter. So what we're going to do is look at when u is equal to tangent x, we're going to look at the tangent of 0, and the tangent of 0 is 0. And then we're going to look at which is my lower limit of integration, and then we're going to look at the tangent of pi over 3. And if you look at the tangent of pi over 3, that's going to be the square root of 3. And so what happens is when I let my u equal the tangent and then I substitute in my limits of integration, I can change my upper and lower limits to match my new substitutions. So instead of going from 0 to pi over 3, I'm going to substitute in my new values, which happen to be 0 and the square root of 3. And now when I find the antiderivative of this guy, I don't have to substitute back. It's already been done. So I'm going to have u squared over 2, and I'm going to evaluate this from 0 to the square root of 3. This is going to be way easier to deal with. And so what this is going to end up giving me is square root of 3 squared minus 0 squared, and this is over 2, and this is over 2. And so what I'm going to end up with is 3 over 2. And that's how that guy works out. And it's a lot simpler then. You don't have to substitute back in. Okay, so let's look at the last example here. And again, you want to look for something that's a derivative of something else. And when I'm eyeballing this guy, I've got an x and I've got an x squared minus 4. And if I'm looking for something that's a derivative of something else, I think if I let u equal x squared minus 4, du is going to be 2x dx. So there's my substitution right there. And notice I got a 2. So since I have a 2, I've got to put a 1/2 in front of my integral. So I'm going to have 1/2 times the integral of 1 over u du. And again, just like with the previous problem, we can take these limits of integration and we can plug them into my u right here. So when I do that, I get 0 squared minus 4. That's my lower limit. So my lower limit of integration would be negative 4. And then my upper limit of integration would be 1 squared minus 4, which is negative 3. And so here's what my new integral is going to look like. So when I integrate this guy, I'm going to have 1/2 times the natural log of the absolute value of u, and we're going to evaluate that from negative 4 to negative 3. And so you just substitute those numbers in. And remember, we're looking for absolute values here. So I'm going to have 1/2 times the natural, let's do this. 1/2 times natural log of 3 minus the natural log of 4. Remember, absolute values. And this is the same thing as 1/2 natural log of 3/4. Remember, if you're subtracting 2 logs, you can divide the numbers inside the logs. So a little practice, you'll be experts.